So what we've been talking about is we've been talking about Taylor series. And when it comes to Taylor series, these are the ones you should know. And there's the generic formula, which says if I have a function f of x, then the Taylor series, that's the sum n equals 0 to infinity, the nth derivative evaluated at a, x minus a to the n over n factorial. Now, we should make a couple of notes here. First note is when we talk about the a here, so the a is where our center is. In other words, we're centered about a. So for any function, you can center a Taylor series about any particular point where the function is defined. And generally speaking, what you're trying to do is saying, let's approximate the function near a. Now, the other thing here is really, we got to be careful when we talk about is equals. Because the function is definitely equal to the Taylor series at the point a. The moral of the story of Taylor series is it's generally speaking, if it's a reasonable function, it's equal to the function around a. Now you might ask, are there unreasonable functions? And the answer is, oh yeah, there are many, many interesting unreasonable functions. And so just be careful. So for the types of functions we talk about, we will actually get equality. You can get things happen in other situations. Now, what do we have? What are the important Taylor series? Well, the first one we saw is 1 over 1 minus c. That's the geometric series. And that's the sum from 0 to infinity of z to the n. It's a very important series. And that's the first one we kind of learned about at the beginning when we talked about series. And it's a good one to work with because it's oftentimes when we're working with Taylor series, we want to do manipulation. So this is our sort of our base example to go off of. Now related to this is the generic 1 plus z to the power alpha. And alpha is any number you want. So it could be like 5, but it also could be like 1/2, and it could be pi. And again, any exotic number. It could be a positive number, it could be a negative number. What's the Taylor series? Well, it's this alpha choose n times z to the n. And remember, the way that you do alpha choose n is the following. You say, look, alpha choose n is you're going to have a product of n things on the top and n things on the bottom. Now downstairs, the product is you get n minus 1, and you keep going down to 1, which I'll write as n minus 1. And really, that means it's n factorial. On the top, it's similar, except instead of starting at n, you start at alpha minus 1, all the way down to alpha minus n minus 1. All right? So that's what the alpha choose n means. Now, what I was talking about, be careful when we talk about this is equal. This part is a place where the equality only holds when we're nearby. So it holds when the size of z is small. If the size of z is not small, then we don't have equality. And generally speaking, what happens is if your size of z is larger than 1, you get things blowing up so that the series don't converge. Even though, if I put in z equals 5 on the left-hand side, that makes complete sense. 1 over minus 4. All right. If I put in z equals 5 over here, it's like, that's infinity. So you have to be careful. Now the good news is for the remainder of the Taylor series that you should know, these ones down here, they hold for all z. In other words, it doesn't matter, what the size of z is. It could be 1 or it could be 1,000,000. It's still true. So the first one is e to the z, which is the sum from 0 to infinity, z to the n over n factorial. So that you can kind of see there's this nice connection between 1 over 1 minus z and e to the z. One of them is just z to the n, the other one has this over n factorial. It has some interesting mathematical implications that you can go into depending upon where your future math classes take you. Hopefully you get to do more math in the future. It's a fun subject. Now the other two are sine and cosine. And these ones you have an alternating series, negative 1 to the n. That's what you see when you see alternating. And other than that, it's similar to e to the z, where you have a power of z divided by factorial. The sine has all the odd powers, and the cosine has all the even powers. The way to remember that, sine is an odd function, so you should have odd powers. Cosine is an even function, so even powers. Wow, it's like it's meant to work, because it does. It is meant to work. It's beautiful. Now, how do we use Taylor series? Now, I would say that generally speaking, there's two big things that we're going to do with Taylor series. So the first thing is, what if we want to find higher order derivatives? Okay, well, why does Taylor series help with that? Well, if you think about how Taylor series work, it's storing information about the derivatives. So in essence, when I have the Taylor series, I have every single derivative I can want at the center. So if I want to know, what's the 100th derivative, what's the millionth derivative at a particular location, I say, well, can I find the Taylor series? And if I can, I look at the right coefficient. Now, what do I mean by the right coefficient? Well, if you think about it, if I want to get the nth derivative, I say, what's the coefficient of x minus a to the n? So that's what we mean when we say the right coefficient. So if I want the 10th derivative, what's the coefficient of x minus a to the 10th? And so forth and so on. All right, so that's the first application. I want to know information about the derivative, and the Taylor series is storing information about derivatives. What's the other application? Well, the other application is to see, hey, you have this sort of equality. So that says, look, Taylor series, I can replace a crazy function by something which is simpler, namely polynomial. And so what we're doing is we can say, I can get ways to approximate what I'm working with. Because oftentimes we don't want to go all the way to infinity, but I can just stop after some point. And what I can do is I can replace my very complicated looking function with a polynomial function, which does a very good, reasonable job of approximation. So essentially, Taylor series help as a stand-in and help us run and do computations. This can also help us get estimates for values, and we'll see examples of what this means in a little bit. Now that's for us. Okay, so our two ideas, we can find nice high-order derivatives, we can get good approximations. In the future, what we might encounter, depending on what we're doing, is we might say, well, I'm trying to understand a function, and I can't figure out what the function is, but maybe I can work with it as a series. So this happens, for example, in a subject called differential equations, where when you try to solve it, you end up saying, this is how it's behaving. I don't know exactly what the function is, but here's the series that it corresponds with. And so one of the things that we're doing is we're developing sort of a sense of how we can work with series. And the better we develop that sense, then the better we're going to be able to figure out what's going on. All right, so we're going to do several examples of how we use Taylor series. So let's begin with the following. Suppose we have f of x is sine of 3x plus x e to the 2x squared. And we want to find the 11th derivative evaluated at 0. Now, there is, of course, one way to do this, which is take 11 derivatives, plug in 0, and then you're done. But that sounds like a lot of work. And that's not why we take calculus. We don't take calculus to do a lot of work. We take calculus to say, how can we avoid a lot of work? So how do the Taylor series come in? Well, one of the things we can say is, hey, f of x, I can say that this is equal to the sum from, say, 0 to infinity, the nth derivative evaluated at 0. And the reason I'm doing it at 0 is because I'm interested in what's happening at 0, times x to the n over n factorial. Now that's just the generic formula. So I say, okay, well that's great. So if I had a way to express f of x in this format, I could say, well, let me figure out the right coefficient. And, well, what's the right coefficient? If I want f11, that's the 11th derivative. So if I come here and I say, what's the coefficient of x to the 11th? The answer is it's f 11th derivative at 0 and divide by 11 factorial. The 11 factorial coming from that n factorial. You've got to remember we got to get everything. And the good news is that's what I want there. Now the bad news is, what do I do with the rest, right? Because I don't know what is that coefficient. And now this is our aha. Let's find our series here. So we have a couple of things. We have a sine function and x e to 2x squared. So we say, well, what do we know? Now we know our generic formula for sine. So sine of something, that's equal to the sum, say n equals 0 to infinity of minus 1 to the n, something to the power 2n plus 1 divided by 2n plus 1 factorial. Okay? That's just our generic formula. And again, I'm saying the something because I'm thinking of it as there's this sort of box. And I can put whatever I want to inside of that box. Now the other function we have here is the exponential function. So what does that say? Well, e to the something, that's equal to the sum, n equals 0 to infinity of the something to the n, divide that by n factorial. And again, I'm thinking of this as sort of a little box. I can put whatever I want here. It doesn't have to be x or z. It can be anything I need. So let's see what we can do now. What we have is the following. So we have sine of 3x plus x e to the power 2x squared. So what we can do is in the first one, I say, aha, it's sine, where the inside is replaced by 3x. So I can say this is the sum, n equals 0 to infinity of minus 1 to the nth power times 3x to the power 2n plus 1. And then we're going to divide that by 2n plus 1 factorial. So that's the sine function. Plus x e, I was going to say e to 2x squared, but let's replace what e is. So plus x times the sum, that's a big dot, right? X times the sum of n equals 0 to infinity. And now our part here, 2x squared, so that becomes the 2x squared to the n, divided by n factorial. Now, the x, we don't need to do anything because x is already a polynomial. We like polynomials. And so once we have a polynomial, we don't have to do anything to change that polynomial. So we stay with what we have. Now I'm going to clean this up just a little bit, not much. So this is a sum n equals 0 to infinity of negative 1 to the n, 3 to the power 2n plus 1, x to the power 2n plus 1, divide that by 2n plus 1 factorial, plus, now this x I'll move in, so that's the sum, n equals 0 to infinity, 2 to the n. Now, as far as x goes, I have x squared to the n, so that'd be x to the 2n, plus one more x. This is really x to the 1, so that's x to the 2n plus 1, and I can divide that by n factorial. Now, if I wanted to at this stage, I could put these together. You may not always be able to do that, so I'm not going to worry about doing that right now. What am I going to be worried about? Well, I said, what's the coefficient of x to the 11th on this side? So I'm going to come back and do the same thing. What's the coefficient of x to the 11th here? So what we're looking for is when do we get something that looks like x to the 11th power? So looking at here, we see, hey, it's x to the power 2n plus 1. So I would want to choose here n equals 5. So I'd get negative 1 to the 5th. I'd have 3 to the 11th. Divide that by 11 factorial. That's from this term. Plus, and then what's the coefficient of x to the 11th here? Now it turns out it's still n equals 5. It may not be, depending upon how your sums work out. It's okay if for one sum it's n equals 5, another sum it's n equals 2. It just depends. So we might see an example like that later. Probably we will see an example like that on the quiz. So, but again, n equals 5. So what do we have? Well, 2 to the 5. And then we're going to have x to the 11th. We don't need that because we're just looking for what's in front. And it's not 11 downstairs, it's 5 downstairs, 5 factorial. There we go. So that's the coefficient of x to the 11th. So what we've done is we've found the coefficient of x to the 11th on both sides. Well, they need to be the same. They have to be equal. So what we get is we get that the 11th derivative, evaluated at 0, divided by 11 factorial is equal to, well, that minus 1 to the 5th, that's a minus. And I like to put minuses in the back, so I'm going to do the first one. 2 to the 5th, I'll just leave that as 2 to the 5th, divide by 5 factorial, minus 3 to the 11th, divide by 11 factorial. Now, I'm almost done. I just got to get rid of that 11 factorial, and that's not so hard. I multiply through by 11 factorial, and we end up getting 2 to the 5th times 11 factorial over 5 factorial, and we'll just leave it in that way. And then minus 3 to the 11th, and here we get 11 factorial over 11 factorial, which is 1. And that is our answer. So there we go. So this is an example of if I'm after a high order derivative, what I can do is I say, you know, my Taylor series is storing information about derivatives, and therefore if I just figure out what the Taylor series is, then I can figure out what my high order derivative is. And this is a case where we say, I don't have to actually figure out what the Taylor series is directly. I can build off of things which I already know about. All right, now let's do another example. Find the limit as x goes to 0 of natural log of 1 minus 3x squared plus 6e x to the 4th minus 6 cosine x divided by x to the 4th. Now, if you plug in x equals 0, you're going to get log of 1 plus 6 minus 6 over 0, which you're probably thinking, this is le L'Hopital. Yes, it is. It is le L'Hopital. So you could do le L'Hopital. Now, if we did le L'Hopital, and spoiler, we're not going to. No, le L'Hopital, oh, mi amor, No, see, here's the thing, is if we did le L'Hopital, how many times would you have to do it? Well, potentially, because you see that x to the 4th, we would have to potentially do this 4 times. And that's a lot of work, because that means we'd have to take a bunch of derivatives upstairs. And you see that 6e x to the 4th, that's going to become really annoying when we take derivatives, because we're going to have to start doing product rules and keeping track of things, and it's just going to cause headaches. And we don't want that. We don't want our head to ache. We want things to be good. So at this point, you're probably thinking, all right, so what's the Taylor series approach? Well, the Taylor series approach is to say, let's replace the upstairs by the appropriate Taylor series and see what we have. All right, so let's see. Now, some of our pieces are pretty good. We know the e to the something. We've talked about that. That's one of our building blocks. Sum k equals 0 to infinity of something to the k divided by k factorial. Okay, easy, easy. Now, cosine of something, that's another important building one. Sum k equals 0 to infinity. You alternate sign, and then you have your even powers. So something to the 2k divided by 2k factorial. All right, those two are freebies. Now, you might say, that's great, but we have something else, namely that natural log of 1 minus 3x squared. Well, how do we do that? And at this point, you're like, well, maybe we can go back to our list, right? Because we had a list at the very start. And if we look in our list, we're like, there's no natural log showing up on our list. That's not a good sign. But wait a second. 1 over 1 minus z. That's something, right? It's 1 over 1 minus z. That's kind of like a derivative of log. And that's the great aha. See, this is not all the Taylor series, but these are the basic ones that we build off of. So let's build off of that. So how do we do that? Well, we can say the following. 1 over 1 minus z. Oh, whoops. I forgot to shade in my little boxes here. Don't forget that. I like to shade in these little boxes. So 1 over 1 minus z. That's equal to the summation from 0 to infinity of z to the k. Integrate, integrate. So integral of 1 over 1 minus z is minus natural log of 1 minus z. The reason that you have a minus is because there's a minus there. And over on this side, you get what? That's the sum. K equals 0 to infinity. You add 1 to the exponent, divide by the exponent. All right, so far, so good. Yeah, that's wonderful. Okay, anything else? Well, remember, if you take an antiderivative, you need a plus c. But how do you find c? Well, the way you find c is you plug in where your center is. We're centered at 0. So when you plug in 0, you get 0 here. Natural log of 1 minus 0 is 0. 0 equals 0 plus c. So that tells us that this c equals 0. Now, how do we finish? Well, let's just say, I'll move the minus across so I can say the natural log of 1 minus z, that's my something, is equal to the sum from 0 to infinity. And I move the minus across so it's minus something to the k plus 1 divided by k plus 1. All right. So now we have our building blocks. All right. What do we care about? Well, what we care about is what's happening because of this x to the fourth. I want to understand these series up through the x to the fourth term. All right. So how do we do it? Well, let's just do it term by term. So the natural log of 1 minus 3x squared. So that's coming into here, replacing the something by 3x squared. So the natural log of 1 minus 3x squared is, when I put in 0, I'm going to get minus something to the 1. Okay, so that's minus 3x squared. And then I'm going to divide it by 1. All right. Now, how about the next term? That would be k equals 1. That would be minus something to the 2. So minus the something, 3x squared, to the 2. And then I'm going to divide that by 2. And then what's going to happen is everything else has higher order powers. So I'm going to say minus dot dot dot. All right. Now, how about the next term, 6e x to the fourth? Well, what will that be? According to this, we have a 6. We're not going to forget about the 6. And e to the something, okay, so the first term would be something to the 0, which is 1, over 0 factorial, which is 1. And there's a 6, so, well, all right, so multiply that, you get 6. That's the first term. The next term would be x to the fourth, right, because it's something to the 1, x to the fourth, or 1 factorial. Then there's a times 6. So that'll be plus 6x to the 4th divided by 1 factorial. And then higher order terms. So when I'm talking about higher order terms, I'm really talking about stuff where it's x to a power bigger than 4. We'll talk about why we stopped there in just a few minutes. Okay, now minus 6 cosine x. So here, it's really easy. That's just cosine x. So the first term would be minus 1 to the 0, and then we have 1 over 1 factorial. So the first term for cosine is 1 times negative 6 makes this minus 6. Now, what's the next term? Well, the next term would be k equals 1. So that would be a minus x squared over 2. So then there's a minus 6. So that's minus 6 times minus x squared over 2. Okay, what's the next term? So that's 2. So that would be minus 1 squared, so that's a plus. X squared, doing k equals 2. So it's x to the 4th over 4 factorial. So we're going to get a minus 6 times x to the 4th over 4 factorial. And then higher order terms. So what we've done is we've replaced each function. We said, what's the Taylor series for that function? So our conclusion is that we get log 1 minus 3x squared plus 6ex to the 4th minus 6 cosine x equals, now let's combine these together. So what happens? Well, the 6 and the minus 6 will cancel out. Okay, so there's no constant. None of these involve x. How about x squared? Aha, there's a minus 3x squared. But let's see, what is this? Minus minus makes plus, and then 6 over 2 is 3x squared. So these terms cancel. So that means there's no x squared term, there's no x cubed term. How about x to the 4th? Well, yeah, there is some x to the 4th terms. So the first term, what do we end up with? Well, we're going to get that 3 squared is 9. So there's a minus 9 halves. Here, we're going to get a 6. All right, plus 6. And how about here? So we're going to get a minus 6 over 4 factorial, which remember that's 4 times 3 times 2 times 1. And then that's all multiplied by x to the 4th plus dot dot dot. Now, here's the key thing. Here's where we care about the dot dot dot. These are powers of x above x to the 4th. So in other words, it's like x to the 5th, x to the 6th, so forth and so on. Now, how does this help us with our original problem? Well, we're dividing it by x to the 4th. So if you were to come through now and divide this expression by x to the 4th, what would you get? Well, you'd get this coefficient here plus this other stuff. And so let's take a second here to read off what this coefficient should be. Now, first off, the reason I did the 4 factorial out, you'll see 3 times 2 times 1 is 6. So we can actually get some cancellation there. So we have minus 9 halves plus 6 minus 1 over 4. That's minus 18 over 4 plus 24 over 4. And then minus 1 over 4. So let's see, 24 and then subtract 19 would leave us with 5 over 4. So what we end up with is that this becomes equal to 5 over 4. The x to the 4th is canceled plus, now everything left starts with at least x to the 5th. And we're dividing it by x to the 4th. So it's x times stuff. And this stuff, that's where the ... comes in. So, by using our series, this is the limit as x goes to 0 of 5/4 plus x times stuff. So we say, aha, that's the limit we can do. That limit is 5/4. Because what happens? As x goes to 0, all this stuff will go to 0. Because if you can plug in x equals 0, you get 0 times stuff. And that's going to be 0. There's no division by 0 going on. So there's our answer, 5/4. Now you might say, that seemed like a lot of work. We filled up a whole page. But a lot of the work was saying, oh, let's recall what the Taylor series are. And then it's just a matter of like, hey, let's combine information about our Taylor series together. And once we got through that, it actually wasn't so much work at all. It was sort of the right amount of work. And so, yeah, that's good. That's good. Cool. All right. Well, that's sort of another example when we want information about the derivative. So how do we use approximation? Well, all right, let's talk about that. So let's suppose we want to do the following. Let's suppose we want to estimate sine of 2. Now, in some sense we say, well, yeah, we know sine for some angles that are nice, pi over 3 or pi over 4. But 2 is not really a typical angle. If you were thinking about this in terms of trigonometry, sine of 2, well, where's 2 at? It's somewhere over roughly here as an angle. So this is an angle of 2. So it's like you're estimating where's the y coordinate for that point. So it's, something, comma, sine 2. It's cosine 2, sine 2. But how do you get sine of 2? So this is a case where we don't have a nice triangle, so it's not just that, oh, we find a triangle, we find the ratio, life is good. But certainly when we plug sine of 2 into our calculator doesn't say, I'm sorry, this isn't a nice angle. Instead it says, okay, here's a number. So where's the number coming from? Well, what we do is we say, we know what sine is. So sine of anything, that's the odd one, so the sum from 0 to infinity minus 1 to the k, something to the odd power, divide by 2k plus 1 factorial. And where really what we plug in here, we can plug in anything because sine is really one of those nice, it converges for all values. So we say, all right, what are we trying to plug in? We're trying to plug in 2. So what we can say is that sine of 2 is equal to the sum k equals 0 to infinity of minus 1 to the k, 2 to the power 2k plus 1 divided by 2k plus 1 factorial. Now, you'll notice, what do we have? This is not an estimate. This is an equality. It's exactly that. So why do we need the word estimate? Well, the problem is, I don't know if we want to add up infinitely many terms. So what we can do to do an estimate is we say, well, let's add up the first couple of terms. So what do we have? Well, this is equal to, and now we just start k equals 0. So remember, we're going to alternate. So just remember plus, minus, and we start with the plus. So plus, then we're going to have 2 to the power of 1 over 1 factorial. So that's 2. Now, that's an approximation if we just use one term. Is that a good approximation? No, it's a terrible approximation. Because sine of 2 cannot be anywhere close to 2. Because sine has to be between minus 1 and 1. So there's no way it could be 2. But that's okay. I mean, it's like we're saying, oh, we're going to use infinitely many pieces, but we'll just take one piece to do the approximation. Of course it's going to be bad. Minus. All right, what's the next term? So now we're going to plug in k equals 1. So we're going to get 2 to the power 3. So that's, I'll write as 2 cubed. And downstairs, 3 factorial. All right, now that's probably a little bit better, but let's do a few more terms. So the next term will be a plus because we alternate sign, 2, and then it'll be to the power 5 over 5 factorial. And the next term will be 2 to the power 7 over 7 factorial. And what would be the next term? All right. Well, first off, let's suppose we just said we'll stop there. So we can say this is an estimate. Now, you might say, why is that an estimate? Well, any place to stop, that's an estimate, that's an estimate, that's an estimate. So we'll just say this is an estimate, and then plus other stuff. Now, the other stuff is 2 to the 9th over 9 factorial plus dot, dot, dot. This is an error. Now, one thing you should always think about is when do I stop? In other words, when is my estimate good enough? And that's not an easy question to answer because it's not so obvious to say, here I can stop because my estimate is perfect. But notice we have an alternating series. So let's do a little bit of recall. So recall, and for alternating series, we have a nice fact. And what's a nice fact? And that is that for alternating series, the error at most the next term, right? Because that's how we were doing that. We jump back and forth, doom, 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 doom. And because you can jump back and forth, the amount you can jump back by is bounded by the next term. So we can say, well, how big is our error? How far are we off? Well, we can say, well, what's 2 to the 9th divided by 9 factorial? Now, what is 2 to the 9th? Well, that's it's a big number. It's 512. All right, so you're thinking, that's a lot of error. Wait a second, we need to divide. What's 9 factorial? Well, boy, that's a good question. What is 9 factorial? That is about, and it's, okay, I'll just use a little squiggly sign. That's about 360,000. Which means the error is pretty small. So if we say the top is about 500 and the bottom is about 360,000, that's about 1 over 700, so 0.005. So that means we're definitely agreeing the first 2 digits for what sine of 2 should be. And notice how many terms do we have here? We only have 4 terms. And within 4 terms, we're going to agree with our first 2 digits. And so this is a pretty reasonable estimate. And if we wanted to agree up to the first 4 or 5 digits, because factorial grows so quickly, it takes almost no time at all for the error to get very, very small. And in fact, with just a dozen terms, your error would be so small that your calculator wouldn't detect it. So that's pretty good. And so this computing sine of 2, it's now not bad at all. And we have ways to do it. Now, you could, of course, simplify this expression, but well, that's all right. We don't need to. Okay. Now, that's a way to estimate. Now, what's another way to estimate something? So suppose you want to estimate the integral from 0 to 1 of e to the minus x squared. And you might say, why would I ever want to estimate e to the minus x squared, that integral? Well, this is a really super duper duper important integral. This is your bell curve. So this is what e to the minus x squared looks like vaguely. And so if you ever heard about standard deviations and things like that, that comes down to understanding what's going on with this function, e to the minus x squared. So this is an important integral to do. And one of the things you may remember is we've said we don't know how to actually find this integral. it's something that we can't find an antiderivative for in a nice way. Now mathematicians will say, well look, we know the theory. The theory says there must be an antiderivative. So, all right, if there must be an antiderivative, but we can't find it, we'll just make up a new function. And so sometimes you'll see there's something called ERF. And so when you see ERF is the antiderivative of e to the negative x squared. But of course, that assumes you know what that function is. We don't know what it is, and so we're not going to do that. So how do we go about estimating? So here's our idea, and it's a beautiful idea, and what we can do is we're going to approximate the function we're going to integrate, and that is the e to the minus x squared by the Taylor series. And so we can, instead of having to work with a function we don't know how to integrate, we can work with a polynomial. So let's go through this. Again, we'll keep writing this down, and you'll see, because we keep writing these down over and over again, you're going to be like, you know, I should probably know these. So I'll use an L. That's a fancy L. Something to the L over L factorial. Now there's no reason to use the fancy L. I just like mixing things up because it's important to remember that the flexibility, that helps us be able to do more. If we always stay too rigid and say, we must use this symbol, we must use that symbol, then we're going to miss out on a lot of the beauty that comes from saying, hey, I can be flexible, I can change names. All right, so here we go. We can say that the integral from 0 to 1 of e to the minus x squared dx, well, we're not going to integrate at first. What we'll do is we'll say, hey, e to the minus x squared, that's our summation from 0 to infinity of, now here the minus x squared, that's what goes into the box. So that's going to be minus x squared to the L divided by L factorial dx. So far we have equality. Now that's the integral 0 to 1 of the sum L equals 0 to infinity of minus 1 to the L, x to the 2L, divide that by L factorial. And again, so far, equality. We've done equals. Now the nice thing is when you're doing a definite integral of a series, wherever it converges absolutely, and for the exponential function, the answer is it always converges, you can push the integral in. So this is the sum, L equals 0 to infinity. We have the constants, minus 1 to the L, that's a number. L factorial, that's a number. Then the integral 0 to 1 of x to 2L dx. All right? So that's attached to L. Now, this integral is actually very easy. If you were to do that, we'll do it on the side here. This would be 1 over 2L plus 1, x to the power 2L plus 1. And you evaluate from 0 to 1. Well, when you plug in 0, you get 0. And when you plug in 1, you get 1 to that times that number. So we get that this is equal to the sum, L equals 0 to infinity of minus 1 to the L, divided by L factorial times 2L plus 1. Now, you might say, hey, wait a second, you said estimate. There's no estimate. That's an exact answer. No estimation at all. So where does the estimation come from? So the estimation comes from, again, similar to what we did over here. It said, well, you stop at some point. So if you start here, you can say, well, what does this turn out to be? So we start with 0. This minus 1 to the L says you're going to alternate, plus minus, and 1 over here, you get that'll be a 0 factorial times 1, so you 1. All right, that's a really weak estimate because we're only using the first term. The next term, we're going to alternate, so minus 1 factorial times 3, so 1 minus 1/3. plus 2 factorial, which is 2, times 5, 1/10. So even 1 minus a third, we're within 1/10 of the right answer, right? Because, again, we're alternating, so the error is the next term. So then what's the next one? Well, okay, so now we're up to 3. 3 factorial is 6 times 7. So that's 42. All right, how about the next term? So that'd be 5, sorry, whoops, got ahead of myself. So this is 0, 1, 2, 3, so the next number is 4. 4 factorial is 24 times 9. 24 times 9 is a number. It's 212. So 1 over 212. So that means we're within 1 over 212. Well, that's smaller than 0.05, right? I think, no, 0.005. Yeah, we're pretty close. And we've only, so that says if we stop there, just go up to that term, we're within 0.005. And so this is a really good estimate. Now how good? How much could we bound it by? Well, so here's our estimate. Whoops, sorry, I'm almost off the screen. Okay, so here's our estimate. And how much is our error? If we went one more term, okay, so this was 0, 1, 2, 3, 4, so the next term would be 5. So minus 5 factorial, it is 120, right? I think so. Yeah, it's 120. All right, good. Did I do this right? 3 factorial times 7, 4 factorial, which is 24 times 9. Yeah, 24 times. Yeah. Okay, sorry. I'm always a little bit worried. Okay, look, we'll be cautious here. So the next term, that's 5 factorial times 11. Now, how big is that? 5 factorial is 120. 120 times 11 is 1,320. So minus 1 over 1,320. So that says our error is smaller than 0.001. So plus ... So this is our estimate. We are within 0.001. And you'll notice all we needed to add was 1, 2, 3, 4, 5 numbers up. And we were able to get within 0.001 of this integral. Now, that might not surprise you, but if you were to try to do the same thing using, say, Simpson's rule or Riemann sums, you'd have to use probably hundreds of computations, add up lots and lots of little tiny rectangles to get the same error. So that the Taylor series, using that as our way to do estimates, is much, much faster. Because it's a beautiful idea that says, you know, we want to do calculus. We love doing integration. We love doing differentiation. We love exploring things. But we run into the things that we can't do directly, like the integral of e to the negative x squared. So let us make everything a polynomial. And that's where we went to. We said, if I have a way to make everything a polynomial, I can now keep doing my calculus because I can integrate polynomials until the cows come home. And so that's what we did. That's what Taylor series was about. Ah, what a beautiful, beautiful ride. All right, that's it for this time. And I guess now we begin the reviewing. We've learned so much. It's time for us to remember what we've learned. So we'll start next time. All right, have a good day. Bye.